Namaste and welcome back to this lecture on mathematical foundations for machine learning. We are doing probability as a part of this lecture series right now. In the last class we looked at the idea of random variables. We said why do we need random variables, what random variables are, and we also looked at some common examples of random variables where we looked at a single coin toss, single roll of a die, multiple coin tosses, then observing number of vehicles that cross through say, a signal and the amount of time that you wait before you, let us say, catch a train from the time you reach the station to the time the train departs. So, we said that okay, you have something called discrete random variables, you have something called as continuous random variables and so on. So, let us continue our discussion on the random variables now. The most important point that we are going to look at here is basically let us say I have mapped the outcomes to a set of real numbers. What do I do with that? That was the question that we wanted to answer in the last class. We said when we completed the lecture, we said that we are going to answer this question. I have done the mapping, where do I go from there? And then we also said okay, how do we attach the probability and stuff. So, that is what we are going to look at now, and beyond that we will also look at how do we characterize let us say a discrete random variable, and how do we characterize, or what is it that we can associate with the discrete random variable to understand it better, and what is it that we associate with the continuous random variable to understand it better. So, that is the kind of questions that we are going to answer in this lecture. This lecture will focus more on the discrete random variable stuff. We will keep the continuous random variables thing to probably the next lecture or the one after that, because I need to cover some basic ideas. Discrete random variables are kind of easy to understand. So, what we do is we try to work with that for some time and then get on to the continuous random variable. Okay. So, let us look at this. So, what do we have? We had let us say from the last class. Let us look at the couple of examples here. I just want you to note something interesting. Look at the example 1 where we had this, where we said that look, I am just going to toss a coin once and count the number of heads in a single toss. And then I said example 3, we said that look, roll a 6-face die once and count the number of dots that come up that are there in the face that comes up. And example 2, I did this, toss a coin 3 times and then count the number of tails in the 3 tosses. This is what we had. Now, there is something interesting that is happening here. If you look at this example 1 where we had omega is equal to the set which contains just the tail and head, there is a 1-to-1 mapping here. Suppose I say 0, this would actually correspond to tail, and when I say 1, this would actually correspond to head, and suppose if I say tail, it would correspond to 0 here, and if I say head, it would correspond to 1 in the range of the random variable. In fact, in the third example where we rolled a 6-face die, when I say 1, I know that the face that came up just had 1 dot. The face that came up, if I say it is 2, then I say the face that came up had 2 dots and so on, exactly 2 dots, exactly 3 dots and so on. That means there also the moment I tell you what is the value of y, I will be able to figure out what is the actual outcome from the sample space associated with that random experiment. That is easy to get. Whereas if you look at this example 2 where I told you, look, you toss a coin thrice, there is a problem here. What is the problem? Suppose if I tell you 0, then I know that all the 3 tosses resulted in heads and no tail at all. I can figure out what was the result of all 3 experiments, all 3 tosses there. Similarly, if I tell you the value that I have got is 3, that means I know that on the coin tossing side I have had all the 3 tosses resulting in tail. Suppose I tell you I had a 1 or a 2, then there is a problem, because there are multiple outcomes in the sample space which had only 1 tail, and all of them got mapped to this number 1 here, and there were multiple outcomes which had 2 tails and all of them got mapped to 2 here. That means this is basically a many to one mapping, right. This is basically a many to one mapping, whereas in the other examples we basically had one to one mapping, right. So, which means in case of many to one mapping there is something interesting. When I tell you that I have got one head, I know that I mean I have got one tail in the 3 tosses, I know that only one of the tosses is a tail. I cannot really tell you which toss was that, right. That is the problem here. When you have a many to one mapping, you basically lose the sequence in which the tail occurred. That information goes I mean that information is lost here, right. A very good example is like you just take a case of an AND gate, a 2 input AND gate where I have inputs A and B and the output is Y. Now what I tell you, I know the truth table of AND gate. So I have A B Y 0 0 0 0 1 0 0 0 1 0 0 0 sorry 1 0 0 and 1 1 1. Now if I tell you that the output is 0, well, there is no way I can tell you what was the input pair that gave me the output 0. The reason is that information is lost. All that I can tell you is like at least one of the inputs was 0 for me to get an output 0. That is exactly what happens here also. You lose information when there is a many to one mapping, right. But there is nothing wrong if you do not want the sequence in which the toss, exact toss in which you have had a head or a tail. I mean if you are not bothered about it, then it is fine. If you are bothered about the sequence, then this would not work. You have a many to one mapping where that toss information at which you got the head or the tail goes missing, right. Okay, now remember we had this sample space, we had this omega. Of course I will take it to be discrete, say let us say I have some finite number of points here. Now what did the random variable do? The random variable basically took all these guys and then it mapped to individual real numbers here, right. Let us say I have some more points here, these two together, let us say this has got mapped here, something like this, right. Now what I want to ask is, I do not want to ask what is the probability of getting head in the second toss. Instead what I ask is what is the probability of getting one head. In a composite case I will ask you the probability of getting one head, right. In which case if you look at the sample space, something interesting here. When I say one head in 3 tosses, either this would have occurred or this would have occurred or this would have occurred, right. When I say one tail in 3 tosses, I am sorry I said head I guess. So this is one tail occurring in 3 tosses. Now what does it mean? Either this outcome would have come or this outcome or this outcome. That means if this first one HTH appears or occurs, I will not have THH or HHT. Same is the case with the other 2 outcomes, which means these 3 events are mutually exclusive, they are disjoint. Therefore whenever I say I want to look at the probability of getting a getting one toss or one tail in 3 tosses, I just need to add these 3 probabilities. I have to add this probability with this probability with this probability, because it is, I mean all these 3 fellows are mutually exclusive. So what I ask is, instead of asking for what is the probability of getting one head or in the second toss, what is the probability of getting a head in the third toss, I will just restrict my question to what is the probability of getting one head in 3 tosses. In which case I am just going to sum up the probability of those 3 events or those 3 outcomes in the sample space, that would give me the probability of getting a 1. So what are we going to talk about? We are going to talk about, we are going to move from the idea of the probability of outcomes to probability of the random variable taking a specific value from its range. So the moment this mapping is done, you actually forget the random experiment that you are working with. So, everything, all the information is now captured in terms of the range of the random variable, and the probabilities are also brought in here by means of the outcomes which correspond to those elements in the range, right. So, what we do is we try to talk about probabilities of the random variable, probability of the random variables taking these values, that is what we are going to look at, right. So, we are going to look at probability of discrete random variables. Probability of discrete random variables. Right. So, how am I going to do this? Remember, my random variable basically took this omega I from the sample space, right, from the sample space, and then it put a real number saying let us say x I. Now, therefore, what I want to do is I want to look at the probability of x of omega I being equal to x I. This is what I am going to ask. So, omega I is basically an element in the sample space, x I is basically an element in the range of x, right, it is in the range of x. So, this mapping I have done. So, now what I am going to ask is probability of x I instead of asking for probability of omega I. So, what is it that we are going to say? This is nothing but the which is given by whatever events that would correspond, say for example, I would tell this probability of x of let us say 2 tails, okay, omega I is let us say 2 tails. This implies I am going to look at x of 2, which is nothing but probability of x of I have let us say tail head tail or tail tail head or head tail tail, okay, that is equal to 2. So, I am going to look at this mapping is now equal to 2. So, I am going to say probability of x is equal to 2, is that okay. Now, how do we get this probability? We are going to say that look, this probability of x is equal to 2 is basically the sum of all these probabilities of each of these events that we have, right. Okay. So, this is clear. Now, what we do is I am going to define a new term here which is associated with a discrete random variable. We are going to say that we are going to give a name for this, p of x is equal to x I. So, what this is basically saying, p of x is equal to x I, we are going to give a name for this. So, let us write this probability of x is equal to x I is nothing but the sum of all those probabilities corresponding to the event, the value x I from the sample space that I have, right. So, we are going to say j, a set of all values j such that x of let us say omega j is equal to x j, where omega j is basically an element here, what are corresponding to 2 that we have here. So, this is nothing but the probability that I am looking for, probability of let us say S j. Substitute over this. Is this clear? So, this is basically the probability. Okay, let me put, we have taken it to be x I. So, let us make this as x I itself. So, what is this probability of x I is equal to 2, x is equal to 2 here implies I am going to have probability of head tail tail or tail head tail or tail tail head, and these are mutually exclusive events, only one of them can occur at a time. So, I am going to write this as p of head tail tail plus p of tail head tail plus p of tail tail head, right. Now, it depends like whether the coin is fair coin or a biased coin, you get the values for the probability of head and tail, and then accordingly you take this up, right. Okay, good. So, now what I am going to do is I am going to define something here which is basically what I call as the probability mass function of a discrete random variable. So, I am going to look at probability mass function which is in short called as the PMF of a discrete random variable, right. Probability mass function of a discrete random variable, basically we will look at what it is nothing but the probability of the random variable x, suppose of a discrete random variable x will take. So, this is nothing but probability of x is equal to xi, which is given by p sub cap x of xi. This is basically a number between 0 and 1. So, this is what we call as the probability mass function. This is the probability mass or the probability associated with the random variable taking the value xi. Is this clear? So, the probability that x takes the value xi is given by px of xi, and this is what we call as our probability mass function or probability mass function. So, the what happens is, suppose if this xi is basically multiple events together form this xi, like what we did in the previous case, add up all the probabilities and you will be getting the probability mass associated with that particular xi value. Basically the mass function says this is the probability concentrated at that particular value xi, right, that is what we have. So, this is basically the probability mass function. So, it says probability of the random variable x taking a value xi is equal to px of xi, which is nothing but a value between 0 and 1. So, let us look at some properties of this probability mass function. Some properties of PMF. So, what is the first one? Since it is a probability number, this guy is a probability number, the first property that I have is 0 less than or equal to px of xi less than or equal to 1. This is subscript I, so do not, so this is basically p of x equal to xi x sub I is basically less than or equal to 1. And we all know that if you take a sample space, the sum of probabilities associated with the individual elements of the sample space must add up to 1, that is what is our idea of probability. We said the probability of sample space is 1. So, the second property is this, the second property is, let us say I is equal to 1 to n, probability sum of all the probability mass function would basically be equal to 1 if the random experiment has n outcomes or when we say our countably infinite case, we can always put this I is equal to 1 to infinity px of xi is equal to 1 for a countably infinite set. Right, this is what we have. And suppose we want to do one more stuff, what is that? Suppose I want to look at, you remember in the case of sample space, let us look at this, let us just take a detour here. Suppose I have this sample space here, let us say this we call as omega, and I have an event A here, and let us say I have an event B here. I mean I am just taking them to be disjoint events, but I can actually have intersection also. What I will do is I will take event A and event B. Now I want to find out what is the probability of event A. Probability of event A is nothing but the sum of probability masses associated with all those outcomes which are defined in event A. So, I will write this. So, we are going to say probability of an event A, probability of the random variable taking a value in the event A, that means having a value from this event A is basically given by you sum up all the probabilities of the probability masses, you sum up of all those xi's which belong to I such that xi is an element of A. Is that clear? So, what I do, I basically take, okay, let us take a simple example. Let us just take a simple example where I have my omega to be equal to 1, 2, 3, 4, 5 and 6. Assume that let p x of x I, or let me say p x of x I is equal to 1 by 6 for x I in the range of whatever x I in the set 1, 2, 3, 4, 5, 6. I would say for I is equal to 1, 2, 3, 4, 5, 6, x 1 will be equal to 1, x 2 is equal to 2, x 3 is equal to 3 and so on, okay, for x I or p x of x where x is in this range. Now, what I do is I am going to define an event A. Event A is nothing but the set of all odd numbers. Now, I ask you what is the probability of A? Probability of A is nothing but the random variable taking a value from this event A is nothing but p of x in A is nothing but sigma p x of x I for x I in the event A. In the event A it can take values 1, 3 and 5. So, what is it that I have 1 by 6 plus 1 by 6 plus 1 by 6 which is 3 by 6 which is half, that is what this means, right. So, we have this as an example for this probability of the random variable taking a value from in an event, okay, that is nice. Now, what we do is, okay, we understood the definition of probability mass function. Probability mass function is nothing but the probability mass concentrated at a particular value of the random variable from its range, right. So, this is what we have. Let us take some classical or important probability mass functions now, right. Important discrete random variables or important probability mass function we are going to look at, which are very frequently encountered, right. So, I am going to look at some important discrete random variables slash probability mass functions, right. I am going to look at this. So, the first random variable that I am going to look at is the following. I am just going to look at a random experiment for which there are only 2 outcomes, and I am going to conduct this, I am going to do just one trial of this random experiment. So, what is it that I am looking for? I am going to model a random experiment with just 2 outcomes, and I am going to model that the outcome of this random experiment with 2 outcomes for a single trial of this random experiment, right. So, what is the condition I am going to do? I am going to look at a random experiment with just 2 outcomes. Only 2 outcomes. The random variable x associated with a single trial of this 2 outcome experiment, single trial of this 2 outcome experiment. Right. So, what are the 2 outcomes that we can have? Okay, we will take omega, you can have head tail, it can be 1 0, it can be success failure, it can be true false, right, it can be yes no. Wherever you have just 2 outcomes, you put that, you can model the single trial, the outcome of the single trial of the 2 outcome random experiment using this particular random variable that we are going to discuss, right. Like your, it is like a binary random variable that you have, either it is 0 or a 1. I am going to give a name for this. This is basically called the Bernoulli random variable or Bernoulli distribution. Bernoulli random variable or Bernoulli distribution, right. So, what is the condition that we have looked at? This is associated with random experiment which has only 2 outcomes, and you conduct the trial only once, do not repeat the trials, just toss a coin once. I want to model the probability of, let us say, success in a single trial of a Bernoulli experiment. You call an experiment, a random experiment with 2 outcomes, you call that as a Bernoulli experiment. So, what I am going to do is Bernoulli trial, I am going to do this Bernoulli trial and I am going to model the probability of success in a single Bernoulli trial, right. So, the probability mass function associated with this. So, let x be the random variable, let x be the random variable. So, we have already told that this is the x is associated with single trial of a this 2 outcome experiment, we have told that. So, let success be equal to 1 and failure be equal to 0. What does it mean? I am going to have a sample space which is going to look at this. This is the sample space that I am going to look at. So, I am going to say probability of x of success. So, what does it do? X of success, that means x is going to take success and then going to give me a value 1. What is this probability? Let me say that probability is p, and probability of x of failure. So, when there is no success, I am going to call that as a failure. So, I am going to call that as 0, and that probability is basically given by 1 minus p. Therefore, let me write the probability mass function PMF of a Bernoulli experiment or a Bernoulli distribution or a Bernoulli random variable is given by p sub x of, let us say, k is equal to p for k is equal to 1. This p corresponds to the probability of success and 1 minus p for k corresponding to 0. So, p is basically the probability of success. This is basically the probability of success. So, how are we going to, the notation is basically, it says x is distributed as Bernoulli with probability of success p, right, Bernoulli with probability success p. Okay. So, we have seen one trial. What is the probability of success in one trial? What is the probability mass function of a Bernoulli random variable we have seen? Now, like our cricket match series, assume that I am going to play this game multiple times. There are lot of questions that we can ask. Bernoulli random variable deals with just one trial and probability of success in one trial. Now, suppose if I continue, if I play this experiment multiple times, let us say 10 times I play this game, I keep tossing the coin 10 times. I can ask, first question that I can ask is, look, how many successes, what is the probability of, let us say 7 successes in 10 times or 10 trials. This is one question that I can ask. What do we do? Repeat the Bernoulli trial 10 times, and in 10 times I can ask this question, what is the probability of getting 7 successes. The second thing that we can ask is, come on, I keep tossing the coin, I want to find out what is the probability of getting the first success in, let us say 10th trial. So, these are questions that we are going to ask. So, first question that we are going to do is, we are going to look at this, repeat the Bernoulli trials n times. So, the question to ask is probability of, let us say k successes in n trials. Example, probability of 7 successes in 10 trials. This is one question that I can ask. Second question that I can ask is, what is the probability of first success at the kth trial. Right, these are the two questions that we can ask, and these are pretty relevant, because say for example I play a 5 match series, I ask what is the probability of team A winning the tournament, the series, right. I ask this question. So, what is the probability of team A winning the series? So, out of 5 match you can either win 3 matches or 4 matches or 5 matches for you to be declared as the winner of the series. So, now I ask you that question, what is the probability of 3 successes in 5 trials, 4 successes in 5 trials, all 5 successes, all the trials have 5 success, all success only. The second thing that I can ask is basically what is the probability of the first success at the kth trial. This is pretty interesting from the context of, let us say, the cricket tournament that keeps happening. So, we ask, okay, we have played so many let us say so many editions of, let us say, World Cup, or probably the IPL trophy, or whatever that is. What is the probability of so and so team getting its first success, let us say, at this 18th edition of whatever IPL that is happening. So, I am going to ask that question. These are both of interest to me, and the answer to these questions we will find out in our next lecture, where we will be dealing with some more distributions like the binomial and geometric distribution. Namaste.